All right. There we go. For some reason my camera is always forgetting its white balance. There we go. So welcome to OpenTapeOut Conference Day 1. I'm Matt Venn, I'm the host. We've got loads of great speakers for you today, as I'm sure you've seen from the schedule. And I just wanted to talk about a couple of things before we kick off with the keynote from Tim Ansell. So first up is Hackaday Remoticon is happening soon, end of November. That's going to be a really great conference. I'm also going to be talking there. I want to say thanks a lot to all the speakers that have agreed to come on this conference and give up their time to do it. So that's really appreciated. Thanks very much. And also apologise to the many people that I couldn't fit in. I wanted to keep the schedule super short and the talk short, but that meant there were lots of people that we couldn't squeeze in. So if you know somebody who would like to present or is interested in learning about this stuff or have stories, then just get in contact with me. I want to say thanks also to all the people on my course who've kind of helped support me in having the time to do this kind of stuff. Just a note or two about my story. So I'm not by any means an expert. I've been using FPGAs for a fair few years. Let me just see if I can share a screen here. So let's start with this one. I remember seeing this a couple of years ago, Adam Zaloof, brother of Sam Zaloof, and you probably know Sam Zaloof as the garage DIY silicon person who did this amazing job of creating some chips in his garage. Absolutely amazing. He was going to be presenting at this conference, but unfortunately he had to drop out. So sorry you're not here, Sam. But when I saw this, I was amazed that ASIC tooling was available open source, and I'd never thought about using it. So I had a go, and I had this FPGA VGA clock running, and I ran it through Qflow, which was a tool run by Tim Edwards of eFabless after I saw him at a conference. And yeah, got a design. I had no idea if it was going to work or not, but it was a design that looked cool, pretty pictures. I think probably a couple of years later, we're starting to get fed up of pretty GDS pictures, but not quite yet. Now we're going to get good die pictures soon. And probably I would have given up then. I was kind of thinking about trying to raise $10,000 to $20,000 to get like 10 people together to do an ASIC, but it seemed like a bit of a big stretch. And then we had the announcement from Tim Ansell over on Fossey Foundation. So that's another big up I should do. Fossey Foundation, fantastic group, and they did the dial-up series. And the first of the dial-up series was Tim Ansell introducing an open source PDK. So it's the world's first open source manufacturable PDK. So that's all the information you need to build an ASIC. Not all the information, a lot of the information, a lot of the missing stuff, and announced this new open source toolchain, OpenLane, based on OpenROAD, which had been going for a few years afterwards. And we'll hear more about that later from Tom Spyrou and Matt Liberty. And also, amazingly, Google is funding free shuttles. So if you want to get involved, the barrier to entry has never been lower. So the tools are open source. If you make an open source design and apply to eFabless, you can even get chips made. And we're just getting the results back from MPW1. So with that said, I'd like to welcome Tim to the stage, who's going to be kicking us off for the conference. So let me just remove this. Welcome, Tim. Thanks very much for coming along.
Hi, it's great to be your keynote speaker today.
Yeah, so thanks very much. I'm just going to exit the room and add your slides. So I'll see you all in. Oh, and there's one thing I should say. We're going to do Q&A. Well, what did you want to do, Tim? Did you want to finish in half an hour and do 10 minutes of live Q&A, or do 40 minutes and move to Q&A on the IRC?
I think we'll see how it goes.
Okay.
I haven't given this version of the presentation before, and so I'm a little bit unsure on how long it will take.
Okay. So yeah, we're running Q&A on IRC and Matrix, and I'll put the scrolly banner up later to give you 5 minutes warning, Tim, when the time is about to run out. And then if anyone's got Q&A, just jump on the IRC or Matrix and ask any questions. So without any further ado, over to you, Tim. Thank you very much.
Okay, hi everyone. So just a first announcement, you can find the slides at this link. It should be at the bottom corner of every slide. So if you're interested in reading the slides, please go and have a look at that. So the first thing you should know about me is that I'm a software engineer. I self-identify as a software engineer. I've been doing software for as long as I can remember. And it really, informs how I think about things. I'm also an open source developer. I've been doing it since, I think about 1994 was the first piece of open source thing I did. And so I've been doing open source for a really long time. And I've also been an employee of Google for about 14 years now. And one of the things that I learned from working at Google is that it runs on computers. They pioneered a lot of this warehouse scale computing, and they use a huge number of computers. People always underestimate how many computers are in use at Google. The thing is, for most of my life, there's been this great thing called Moore's Law, which meant that if you just waited a couple of years, all of a sudden, all your software got faster. That's started to slow down and started to be less successful. Although if you go and talk to Intel and TSMC, maybe they would disagree with me. But one thing that hasn't changed is that the demand for compute continues to grow pretty much exponentially. And to keep up with this demand with Moore's Law slowing, Google has had to look for alternative solutions. And one of the solutions that we've been very successful with in the machine learning space is the TPU. And the TPU is an accelerator that dramatically speeds up machine learning. The problem, though, we discovered when doing things like the TPU, and this is well known in the IC creation industry, is that as you go to more advanced nodes, the cost of creating the design and the verification increases substantially, and the cost is continuing to go up. As well, the difference between what you should get in theory from a new process technology and what people are actually able to achieve with that process technology is increasingly having a gap. And as I said, I'm an open source developer. And so I thought, well, could there be something to having open source silicon? And so when you think about creating ASICs, I like to think there are three major parts. There's the IP libraries, and there's actually quite a strong history of open source IP libraries. The FOSSI Foundation, which was mentioned, has been around for a long time. It was very involved in the open risk thing. There's been open cores. And recently, there's this been massive explosion in open source IP and RTL based around the RISC-V ecosystem. So we've got quite a lot of open source IP. There's actually also a long history of open source EDA tools. One of the EDA tools that you may have used in the programs that I run is a tool called Magic that's currently maintained by Tim Edwards. That tool is older than I am. And it's actually so old, when I went to go and look at what license it was under, I discovered that it predates the standard BSD license. So it definitely has a BSD license these days, but there's a strong, long history of open source EDA tools. But the last thing you need is PDKs. And when I started this, I couldn't find open source manufacturable PDKs. And this surprised me because, it's been a very long time for many of these process technologies, and I would have expected somebody to have developed this. And when I looked around about, what is a PDK, because again, I'm a software developer, it contained all the low-level information about what you need to make a chip. And this seems to me like the type of thing you need to get anything useful at all. And so I had to search for things like what was out there. And there were some manufacturable PDKs, but they were on very, very old process nodes. And there was a bunch of other stuff that was under restrictive licenses. Although since I've started in this area, we've definitely seen a slow change in things actually becoming open source now. The reason this is problematic, though, is if you look at the Fabless Rovana chip, they had fully open source RTL, they used fully open source tools, but they used an XFAB 180 nanometer PDK, and the XFAB 180 nanometer PDK is not an open source PDK. And so if you think about it, this PDK data, because it's so fundamental to the manufacturing, infects the rest of the design and makes it pretty much impossible for them to release something that other people can reuse without having to think. And this hole was a really big roadblock I identified. And so I came up with a plan to solve this, and a plan that I thought was going to change how we do IC design and potentially solve some of those issues that I was talking about with Moore's law ending. The plan had three parts. The first part was we release an open source PDK, we fund some EDA tooling integration, and then we have a silicon realization program. So the first part was, release a PDK, do EDA tooling integration, and run a shuttle program to get people into the community. And one of the key metrics I was looking for was number of users. How could we dramatically increase the number of people using tooling, the number of people writing IPRTL, and the number of people using the PDK? And something that I discovered is that in the US, some estimates put us around 70,000 hardware engineers, growing at 6%ish, which is a pretty good growth rate. But there are 800,000 software engineers, and that's growing at 30%. And that is a much bigger pool of people and a much larger growth rate. And so the other thing that I really wanted to focus on is how do we make software engineers into hardware engineers? So that was the plan, the hypothesis I had. So how's it going? Well, part one was getting this PDK or a PDK that was manufacturable released. And experts in the industry told me this would never happen. You would never be able to succeed at doing this. And then in June 2020, I surprised everyone with this open source PDK. I did the first talk about it at the FOSSI Foundation, and this is a fully open source PDK. It's available on GitHub. You can go to this URL and you can use it for manufacturing. It's under a real open source license. It's under Apache 2 license, and you don't have to sign NDAs. You can just clone. This is a fairly old process node. It's 130 nanometers, but it has a lot of nice features. It has the ability to have 5-volt I/O. It has a lot of extra functionality like MIM caps and Sonos shrunken cells. and a bunch of high voltage support by default. It's a very all-inclusive process technology. And as part of that, we were also able to take the documentation that's normally delivered as giant PDFs and publish it as searchable, readable, HTML documentation that just anybody can look at. Here's kind of a screenshot from an earlier version of it. And here's an example of the documentation. And we can include things like this stack up diagram, which if Matt can make that giant pop-up go away, maybe you can see the full details about. Well, that doesn't appear to be happening, so I'll just continue. If you look at the process technology, you can go and look at this stack up. It also includes a bunch of different standard cell libraries. And these standard cell libraries are actually quite comprehensive, and they cover a wide range of different types of use cases. You can see here a spreadsheet that I did to try and figure out, which cells are available in which libraries. We also, can publish, generated schematics and symbols, and we can even publish the GDS. And so today we have available, the digital standard cells, we have IO and periphery cells, we have primitives and DRC things, we have analog primitives. I know a lot of people have been waiting on this, but we have build space for SRAM available now. And hopefully in the next couple of weeks, we will also have a ReRAM PDK that enables you to use ReRAM on MPW4. This open source PDK data, I believe, is really important to filling out that fully open source ASIC result. And it appears that a lot of you agree with me, because in the first week after the PDK was released, the PDK got almost as many stars as traditional hardware projects like Yosus and Chijul, some of which have been around for 10 years. And if you look at the download stats, and these download stats are quite old now, but I haven't had a chance to update them, there are 200-ish new users on the PDK every week. If you told somebody in industry that they were going to get 200 new users every week on their PDK, they would tell you that there's no way that's going to happen. It's also seen a massive increase in the number of users, downloading tooling and being involved in tooling. We also have this massive community now that every time I give a talk, I have to update this slide because it's gotten bigger. There's 2,100 members on this Slack space that anybody can join, including you, and there's a big community there. This is just the start, though. The current PDK is a start. We need to continue to expand it. We're still trying to figure out how to deal with pull requests. There is, a whole bunch of pull requests there pending that I'd really love to get merged, but there are certain complications around that. And, the PDK data could use a lot of love. So we have partnered with NIST to do a recharacterization of the Sky130 process technology, including characterization over wide temperature ranges. We're looking at, in 2022, having fully open source cloud-based TCAD for Sky130. And I think this is super interesting because it expands the PDK's capabilities to areas that are traditionally underserved, like silicon photonics, quantum, and, we can even start exploring having things like carbon nanotubes and some of the other technologies Skywater has available. So I think the open source PDK release is going really well. What about part 2, the tooling integration? So for tooling integration, I had a focus on this groups of projects. And in terms of digital ASIC tooling, I strongly focused on the OpenROAD project. The OpenROAD project has its majority of its funding through the DARPA program, and I helped supplement some of that funding. As well, eFabless took what the OpenROAD project was doing and built OpenLane, which was strongly focused on Sky 130. DARPA really wanted OpenROAD to focus on GF12LP, which is a very advanced node that isn't open source. And so we were able to provide supplemental funding and work with eFabless to create OpenLane, which was very focused on the needs of Sky 130. As well, we worked with the OpenROAD project. And if you have been waiting, the SRAM bit cells have actually been live for a couple of months now. We just didn't really announce it. You can go and look at them. But the bit cells by themselves are not actually that useful. You have to combine them into arrays, and there are certain requirements around how you combine them into the arrays to make them manufacturable. And so Matt Goodhouse with OpenRAM has developed a memory compiler. He gave a talk about it at the FOSSI Dial-Up series, and that continues to improve and continues to iterate on that. And this is a fully open source project. You can go and help improve the OpenRAM project and help improve our SRAM capabilities. As well, one of the key things was, how do we improve analog automation? And so I had 2 areas that I was looking at. One was FASOC from University of Michigan. When I started, FASOC was mainly focused on the proprietary tools. But thanks to some excellent work via MEDI, there's now an open FASOC which replaces all the proprietary tools with open source tools. And they have been successful in taping out designs in multiple MPWs. The first one, they focused on having design for an LDO and a mesh of temperature sensors. The second one, they went even further and started doing an analog mixed signal SOC, and used the OpenTitan RTL from Google's OpenTitan project to build a full mixed signal SOC using fully open source tools. They also have exciting things like continuous integration that includes automating checking of DRC and LVS errors on their repo. And I think this is a really exciting change for how we think about analog design. And, you know, the CI is now working for the temperature sensor and evolves a whole bunch of different work, but I think that's really cool. The other analog generator that we were looking at was the Berkeley analog generator from, Berkeley, or BAG as it's called. That has been less successful. At the moment, there are primitives available for use with BAG, but BAG still requires closed source software and Skywater's proprietary S8 PDK, which was the thing that existed before the open source PDK. Berkeley is actively working on producing a digital PLL generator and a SAR ADC generator using BAG, and the output of those will be usable on the open source PDK. But for now, you need access to these 2 pieces of technology. There's also many more. And if you think about the whole ecosystem, here is one attempt for me trying to draw a map of it. And what I'm really focused on is fully automated tools with open source PDKs and building out the IP ecosystem that covers that. And as I've been doing this, I've evolved my thinking a bit. As you can kind of see, my initial thinking was around tooling, IP, PDK. But the more and more I got involved in this, the more and more I started thinking about it from a software point of view, where you have the interface with the outside world that can come in digital and analog. You have the computation work, which is things like CPU and custom, digital logic. And then you have storage, which is things like memory and flash.
About fault injection attacks and how to defend against them.
I think there was a little bit of a mistake there. But as I was saying, you can think about this in terms of the needs of design. And so if you think about EDA tooling integration, you can start thinking about it in this diagram, where instead of thinking about them as separate things, you think about how do you use them. And so I think the Open EDA tooling integration is going really well. And lastly, the Silicon Realization Program. So we announced this open source shuttle program, and as Matt mentioned, it's a no cost to the developer. But what you do have to do is your design has to be fully open source down to the GDS. There are but roughly 40 slots per run, and you submit your design to eFabless, and it gets included in the MPW runs, and they handle all the manufacturing, distribution, all these type of things. To make that possible, though, there is a standardized harness, and the standardized harness allows us to get you back a large number of packaged I/O. Package parts. You get 10 millimeters squared that you can do whatever you want with, and the harness there enables you to have a lot more debug functionality, even though things like the I/O pins are much more limited and need to be configured in a certain way. So this has been evolving, and I expect it to continue to evolve and get more functionality. And so recently they added support for if you wanted to do analog design without them needing to do custom work. And one of the key things about this is we don't want your prototypes to be uniquely precious. Traditional MPW programs, you get back maybe 5 or 10 ICs. They're definitely normally raw die, which you then have to go and figure out how to package, which makes it very hard to share your results. It makes it very hard for you to group a lot of projects together. It also makes it super expensive to do lots of versions of stuff. And we really want people to try and fail, but then try again. And so how has the MPW program been going? Well, at the end of last year, we had MPW 1 go out. Middle of this year, we had MPW 2 close. And then there have been a couple more that are happening now. So MPW 1 finished, and there were 45 designs submitted for the 40 slots from 76 designers on MPW 1. And 60% of the designers on this were first-time designers who had never done a design before. And it covered a huge range of different types of designs. I was honestly surprised at how much variance there was in what people were doing. There was a lot of socks, that was expected, but there are also things like amateur satellite stuff, robotics apps, things like this. MPW has also closed out, and the thing about MPW 2 is 1/3 of people doing projects on MPW 2 self-identified as software developers like I do. And I think that's a really important change in, what this program is enabling people to do. Based on the Google program, eFabless also launched a commercial program. So if you don't want your design to be open source, or you have other requirements, like you don't want to be restricted to the style of packaging that the Google program has, you can go and put your design in the commercial program, and it's very cost effective. It's based on a lot of the learnings we've had from the OpenMPW program. We're also seeing some really awesome things, like Matt Venn, who's running this conference, developed this multi-project tools. And these multi-project tools are compatible both with the Google MPW program and the eFabless ChipIgnite program. This means, with the number of ICs we get back to people, that you can have 16 projects in one slot and everybody still gets 5 ICs. If you take the cost of doing a private MPW with the ChipIgnite program, that makes it less than $1,000, about $610 per project. And so if you look at our schedule, this is kind of what it looks like. And I want to be clear, it's not too late for 2021. There is MPW 3, which I think has another week before it closes. Then there's MPW 4, which will probably close at the end of December, if I understand correctly. And there will be more in 2022. But I highly suggest that you get your design in every MPW. You should be submitting your design every time you can. So, as I said, the third run was supposed to end in October, but it's kind of pushed out a little bit. The one will go out, MPW4 will go out in December 2021. There'll probably be 4 runs in 2022. And the interesting thing is MPW4 will add the ability to use ReRAM. So if you ever wanted to try ReRAM in your designs, then MPW4 will give you that ability, and the PDK should be out in the next week or 2 that enables you to do that. So what are the plans for the future here? I think we've been quite successful. We're looking to add a second foundry and expand more programs that have a similar style, no-cost MPW program. And the one that's most likely to happen next year is a second foundry with a budget 180 nanometer process. I know 180 nanometer is an extremely popular process, and it's likely there'll be 3 runs of that next year as well. So not only will we have the 4 Skywalker 130 runs, we will also have probably 3 180 runs next year. So there's going to be plenty of opportunities to do tape outs. As I mentioned, we're also trying to build up the capabilities for doing a lot more advanced stuff with things like TCAD. And we really think that this OpenPDK is enabling IP and tooling to advance significantly quicker than what it was previously. The delta in quality of the tools between MPW1 and MPW2 is absolutely massive. And we've seen a huge amount of really interesting things done by the community. And so this is kind of the call for help section. My team here at Google is only a small team, and we're trying to do a lot. And, we're not an ASIC design team. We're a software team trying to do new things in new ways that have never been done before. We're working with a lot of partner organizations, people like, the Open Titan and Low Risk and FOSSI Foundation, the Open Compute Project, CHIPS Alliance, RISC-V, Open Power Foundation. We're also working with a huge number of academic partners. If you want to be a partner, key things is that you shouldn't be using proprietary tools or proprietary PDKs. And the most important aspect is creating an open source project. And for everybody on the stream, you can help. As I mentioned on MPW1, 60% of the submissions were from first-time designers. And I want to be really clear is it's okay to fail. Doing new things is hard. You will fail sometime, and you should try again. The reason we don't have just one MPW run is because we want to see people try stuff, learn from it, and improve. So this is a really important aspect, is that we are going to see people not create successful working chips, and that's okay. If you continue to learn and you continue to iterate until you get to a successful working chip, that is 100% working as intended. And so I do think I also want to mention is that there's been lots of surveys from groups like Siemens about surveying professional ASIC designers, and less than a third succeed 100% on their first design. And these are people who have been doing this forever with tools that are extremely expensive and extremely large teams. So it's expected that things are going to take a while to improve, and they're going to take multiple attempts to get right. It's going to take multiple attempts to get right. And that is the expectation here. I come from a software world. My software never works first time. It probably doesn't work, the 100th time I run it. And so this is perfectly fine. I would like to see a lot more iteration. So if you want to get notified, there's a mailing list you can join, and there's the Slack space. I do want to encourage everybody to come and join the Slack space because there is over 2,000 people there. It's also bridged to IRC if you have some type of objection to Slack, but only the main channel. And there's lots of activity going on there. There are groups focused around analog design. There are groups focused around developing new courses. There are groups focused around RISC-V. And so that's the end of my talk. And I think we might have time for questions. Matt, is that correct?
Yeah. Let's go for some Q&A live while we're waiting for the next speakers to arrive. So feel free to write anything in the YouTube or the so I'm just getting confused with audio feedback from the laptop or in the Matrix or IRC channels.
Do you see any questions there, Matt?
I'm just scrolling up. Maybe Stefan, who's lurking on the stream, could scroll back and give us some that we've not already answered. One thing that I would like to know a bit more about is you mentioned ReRAM, and I think that stands for resistive RAM, but could you explain a bit more what ReRAM is?
That's about the knowledge I have. As I said, I'm a software engineer. I know it's a technology that is particularly useful for certain types of designs. It can be very useful for creating things like Flash. It can also be very useful for creating things like FPGAs. There's a lot of papers published about how ReRAM really can increase the performance of FPGAs on, sorry, I lost my train of thought then.
But essentially, resistive RAM is like a bit like Flash. You can put write data to it, and then it stays there when you power the chip off.
Yep.
Is that right? Okay. We've got some questions saying, are there any plans for future smaller nodes like 90 nanometers?
Yep, there are. There are definitely plans. I have proposals around multiple different 90 nanometer nodes. I'm in discussion with a group about a 65 nanometer node. But, these things take time to do. And while the cost of running things like the Skywater program are actually quite cheap, compared to, say, doing a 12 nanometer node tape out, I think the whole Skywater program is significantly cheaper than a single 12 nanometer mask set. There is, I need to find funding for it, and I need to work through the legal things. And the silicon industry is not a particularly fast-moving industry. I would have loved to have the 90 nanometer stuff released already, but it's still pending on a bunch of things happening that are moving forward, and it's just not there yet. And a lot of these things I can't know when they will happen. Negotiations take time. So yeah.
Okay, yeah, so we've got another couple of questions. What is some EDA tool that is still missing from the free and open source flows that we have at the moment?
I'm not the correct person to ask that. Sadly, I have not had any time to do ASIC designs. I now spend most of my time doing things like presentations and reviewing funding requests and working with companies to try and get more PDKs released, and that consumes all my time. Submitting budgets to my employer and things like this to get approval. And so I don't have a good understanding necessarily of what's missing here. Analog stuff, I know a lot of analog people think there are things missing. I'm unclear whether those things are actually missing or they're just not documented well enough that people know how to use them. I definitely think like, the FASOC project from University of Michigan and the OpenFASOC project, is doing some really interesting analog stuff, and none of that needs a lot of the tools that analog designers traditionally say are 100%, necessary. And so, like, there are also alternative solutions to these problems that people are looking into, and I think that's really exciting. Restrictions are kind of the mother of ingenuity, and
Mother
I think
of invention.
Yep, things like that. I have not the best pronunciation of anything, so I'm sure people know what I'm talking about, though.
Yeah, and it's pretty early where you are as well, isn't it? So thanks for getting up on your weekend and joining us on OpenTapeOut. So if you've got any more questions for Tim, then feel free to jump on the IRC or the Matrix, and let's all give Tim a thanks. Put a thumbs up or a thanks in the YouTube comment, and Tim, I'll see you about on the Slack or in the IRC. Thanks again.
Thanks.
So what have we got next? We have got an update on OpenROAD. So probably if you've been following my channel at all, you know the tools that I'm most using for doing my ASIC work is the OpenLane tooling, and the absolute central part of that is based on OpenROAD, which is a DARPA-funded ASIC tool flow that's open source. And recently, well, it was maybe about 3 or 4 months ago, OpenLane was developed by eFabless and Google, and then that has kind of been moved into the umbrella of the OpenROAD project now. So if you go on the GitHub, OpenLane is now hosted under OpenROAD. And we're very lucky to be joined by a couple of OpenROAD developers now. I'm just going to add to the stream Tom. How are you doing, Tom?
Good. How are you, Matt? You hear me okay?
Yeah, looking good. Stream's looking good.
Great.
We spoke one time before on an interview that I did for the Zero to ASIC YouTube channel. So if you want to check that out at some point, feel free to look at that. And as I understand it, Tom, you're going to kind of give us a bit of an update on what's been happening in OpenROAD. And then we're going to have a little demo of some of the GUI tools from Matt Liberty later, who's another OpenROAD dev.
Yeah, thanks. That sounds really good.
So I'll pass over to you. And if you add your slides, then I can add them to the stream if you need them.
Got it. Okay, so I'll start by sharing my screen, and then where would I'll talk with you later about where to add the slides.
You do them with the little button at the bottom where it says plus share.
Yes, got it.
There we go.
Okay, is that good?
Very good.
Cool. Okay. Okay, so thanks for having me, Matt. Thanks everybody for joining. I want to talk a little bit about OpenROAD and really updates of what's been going on since pretty much over the past year I'll talk about, but I'll focus maybe more on the past 6 months. I just wanted to say I'm Tom Spyrou. I'm presenting. I'm the chief architect of OpenROAD and a UCSD visiting scholar as part of the DARPA program. Matt Liberty will follow me in this session and give a demo and answer detailed questions. So thanks. So I think the first thing is, why are we here? Why did DARPA fund this program? Why are we trying to do OpenROAD? So I think if you look at how ASIC design is done today, everybody knows that they're very sophisticated proprietary tools with thousands of commands. And the focus of the tool suppliers is to maximize performance, power, and area. That sounds like a good thing, but the focus of the tools and the usability and the commands is all around that. Whereas with OpenROAD, we really want to have the main focus be on automation, but also have reasonable power, performance, and area. So it sounds subtle, but it's actually a big difference in focus for the tool. So today's ASIC teams need large teams of expert users with many manual steps involved. There's long project schedules and significant project risks. So the goal of OpenROAD is no humans, 24 hours. And again, the focus is to maximize ease of use and runtime and to directly attack the crisis of design and innovation. And that crisis is that it's just getting more and more expensive to design chips. And so there are lots of chips that people would want to design, but that are not getting designed. Perhaps they leave it in software, perhaps they do it with an FPGA, whatever it might be. So there's a schedule barrier that we're addressing with RTL to GDS in 24 hours, an expertise barrier, no human in the loop for tape out quality GDS, and a cost barrier. The tool is open source, and with all the good work that Tim is doing, there are open source PDKs coming online, and it runs in 24 hours. So what we want to do is unleash system innovation, let people design those chips that they're blocked from shipping today. And if you paid attention during Tim's talk, that's a main focus that he talked about as well, that I think he said 60%, I thought that was the number I heard, of people have not done chips before. And that's what we're after, unleash innovation. Make it so that if you have a great idea, you can design a chip in your garage, just like you can write a software program in your garage. So I think looking at OpenROAD version 2.0, version 2.0 came out probably in July or August, and I'm talking mostly about what's in there and a little bit beyond. The new features that we've added is an early SOC planner. So if you do want to look at your floor plan or somehow be manually involved with that, you can. Also, we're working on improving the macro placer and making sure that the fully automatic floor plan has even better results. The next thing that we added is also parasitic extraction and using that for timing sign-off. And that's really important. Previous to having the OpenRCX extractor, the timing analysis that was done in OpenROAD was done with placement-based parasitics. And those are great estimates, but as you get to lower and lower technology nodes, you really need to know what layer the wires are on to do a good timing estimation. So we're very excited about that. Usability, we have a document on how to bring up tool on a new technology. We're making it easier to bring up a tool on a new technology. We've improved the messages and documentation a lot, enhanced user GUI. We've also focused a lot on power, performance, and area. Like I mentioned, our initial goal was automation at all costs, DRC correctness every time, all the time. And so now that we've gotten over that hurdle for the most part, as Tim said, with any software system, there's always some tweaking and tuning that has to be done. So we are now turning our attention to PPA. So here, initially, we've been focused on logic synthesis, placement, clock tree synthesis, and timing optimization. So for a lot of our benchmarks now, if you compare our version 2.0, the designs are coming out 30% faster and 20% denser than in version 1.0. So that's basically a whole technology node of improvement. The next thing too is that we're moving forward on what we call the true no human in the loop flow, or auto tuner, which uses machine learning to launch multiple runs of OpenROAD with various parameters. For those who are familiar, it's using hyperparameter tuning in order to do lots of runs of OpenROAD to come up with the best PPA. So we're really excited about what we've been doing with version 2.0. I think we've probably talked about it enough that in Sky 130 through eFabless on the Google-sponsored shuttle, there's been more than 100 tapeouts. eFabless has their Chip Ignite shuttle. We also do support some closed source PDKs. You have to talk to the Foundry if you want access to those, but for the ones that we do support, if you get access to those Foundry PDKs, you can use them with OpenROAD. So in GF12, there was a mixed signal tapeout that was done that I'll talk a little more about. In Intel 22, there's work on an AI device. So at the moment, we have test cases running on GF12, Intel 22, GF55, TSMC 65, Sky 90, and Sky 130. And we have more nodes on the way. And part of the reason we want to be sure that we support multiple nodes, especially ones like GF12, which are fairly advanced, is one of the goals of OpenROAD is to document for posterity the right way to architect and build an EDA system. So we don't want to build something that's only good for old nodes. We are very focused on making sure the system can support all of the advanced nodes over time.
Tom, could you go into presentation mode on your slides so we can fill the screen with them?
I wasn't sure what would work better. So does that look better?
Yeah, it looks better.
Okay, sorry. Thanks for letting me know about that. So one thing that we're pretty proud of is we did what we call a tape in. We made the manufacturer GDS. We got it all the way through Caliber and the Foundry tests. We just didn't have the budget to actually fab it. So we did a 12 nanometer SoC tape in called Black Parrot. We did a version of that with version 1.0 of the software. And using version 2.0, we've been able to see a 36% increase in Fmax, a big improvement in total negative slack. Maximum skew is a lot better, total wire length. So on all parameters, we're really happy with how this is going. This was done in Global Foundries 12LP using Invicus IOs and the ARM standard cells and RAMs. The GDS is DRC LVS clean as verified by design advisors using Mentor Caliber. And we were able on this design to go RTL to GDS in less than 5 hours. So another PPA vector that we're working hard on, and I know there's been a lot of discussion about that, in earlier versions of OpenROAD, the clock skew was left something to be desired. So by making improvements to how we partition the clock tree and improving an algorithm called sync cluster, newer versions of OpenROAD have much better clock tree synthesis and much better clock skew, as you can see here. As expected on large designs, you will see a good bit of latency. And so in your timing sign-off recipe, you have to be sure to put in proper on-chip variation to compensate for the skew that's part of that and have it show up in your skew calculation in your sign-off timing report. So here you can see the clock tree. Now the GUI, which Matt will give a demonstration of when I'm done, you can actually visualize the clock tree, make sure that it looks balanced, make sure that especially clock trees leading up to discontinuous things like macros look good. And you can actually view timing reports in the GUI now. So if you see a timing path that is failing hold, for example, you can visualize it in the GUI and figure out what you're going to do about it. Normally, users should not have to intervene in this way, but as we're building up the software and making it better, it might happen that you see a failing timing path, and it might be good to look at it. So another thing that I mentioned, the auto tuner, is that we're working hard on synthesis and automatic PPA exploration runs. So at the moment, we have 22 synthesis optimization recipes with 7 main configurations, 4 dedicated to timing and 3 dedicated to area reduction. For example, their buffering sizing options include tweaking the max fan out parameter, tweaking your max transition constraints, upsizing and downsizing. The default OpenROAD recipe here is shown in red. And so what we've basically been doing by running these experiments, we've been changing the default OpenROAD recipe, making sure that when you run it out of the box, you can get the best results. And then, of course, on top of this, in the future, when we release AutoTuner, you would be able to spawn lots of runs and use machine learning to improve this even further. So for post-synthesis automatic PPA exploration, a lot of work has been done in this area. There's even an ICCAD paper, I think, that's been published about this. So here what we're trying to do is analyze and improve what we call QOR trajectories. So as OpenROAD is running from RTL to GDS, at each step of the process, we do analysis based on various cost functions like area, timing, wire length, congestion, etc. And so what we're doing with all of these experiments is doing an exploration to figure out where do we set these parameters in order to get the best results. And using machine learning and AutoTuner, we're going to automate these experiments so that if someone brings up a new node or has a design that's a lot different than we've ever done before, these parameters can be automatically tuned as the flow progresses and improve results quite a bit. So as part of our commitment to machine learning and AutoTuner, we've standardized the AI metrics for an EDA flow in order to facilitate tool learning. So for example, metrics could be the number of buffers inserted, the total wire length. Runtime metrics are kind of more obvious, CPU time used, peak memory used. And all of these metrics can become features for training machines. So one thing that we did is we moved all of the code to use a unified logger with consistent namespaces, consistent information, warning, critical message, nomenclature. And this is essential for continuous PPA improvement. We need to have automatic tests that run. We need to make sure that they're always getting better. And we can use these same parameters to train machines in order to do machine learning runs and improve results. So there's some, for each design stage, there's various metrics that we gather, floor planning, global placement, CTS. There's metrics categories, area, congestion, timing. And then, of course, there's the metric itself, total negative slack, worst negative slack, number of instances, switching power, CPU time, etc. And so all of these parameters can be used to train machines, and you'll see them in the log file. So I think here's an example. You probably, if you look at the log file, which you shouldn't have to in a no human in the loop flow, but if you do, you can see these metrics there, and they can be parsed by anybody who wants to try to use them to train machines and run OpenROAD with machine learning. So we've had a couple of other exciting designs, ones that were not related to 130 nanometer node or eFabless, that I thought it's good to highlight. There's a user who doesn't want to be named who's done an AI platform and various experiments with different AI tiles in GF55 and GF12. There's University of Michigan. The FA SOC program has done an OpenTitan SoC with GF12 LP. And so we're very excited to see all of the good work going on with the open source PDK and also all the work going on with the closed source ones, which hopefully one day will become open source. I think that Tim talked a lot about this, so I won't go into any detail on this, just to mention that we're very excited to work with eFabless on this. The 100+ tape outs is just great. And this is where the bulk of our users are. So we have a lot of focus. We're working closely with eFabless to make sure that this flow is streamlined and works well. We definitely do have a growing user community. I think that this just basically shows a 2-week random period that I picked, and we had almost 14,000 clones, which I think is great. That means people are downloading the software, kicking the tires. And we know that the different applications people are using it for, root of trust devices, people want to enhance it to do 3D IC, AM, ML. The community metrics are all growing, which we're really happy about. So I think in terms of availability, most of you know that the OpenROAD project is the area where we're hosting things. OpenLane is the automatic flow developed by eFabless. And the top level application called OpenROAD is in the repo at the bottom. And to kick the tires, you can play around with OpenROAD if you're trying to learn about EDA tools. But I believe most users will use OpenROAD in an automatic flow like OpenLane. So kind of to summarize, in the past year, we've had a lot of breakthroughs. We've had a 12 nanometer tape out. We've proven we can do tape outs at 12 nanometer directly from an academic research effort. We have an integrated architecture, the database, the timing engine. So this architecture is built to last. In version 2.0, we've improved PPA a lot, like I mentioned, the machine learning and auto tuning, the 100 tape outs. And we have a lot of engaged contributors, which is great, from IBM, Google, eFabless, and others as well. So I think in terms of keeping this project to be sustainable, what we're really hoping is that eventually we want to figure out how does this sustain itself, either companies like eFabless building a sustainable business on it, and also having a research ecosystem. Businesses would productize, distribute, support, like you see eFabless doing. Hopefully the research ecosystem will innovate and make the tool go faster, make the clock frequency go faster. And then special applications and system needs could also be better served. In terms of growing the technology, machine learning, cloud, I think cloud deployment is really an interesting area for this. For something that's fully automatic, people may not want to go through the trouble of building, installing the software, etc. They may prefer to run it in the cloud. So that's something that we're talking about and working on. And of course, we want to grow the user and developer community. That's something that's super important to us. So we are looking for users and developers to join the effort. So if you work for a company that would let you do it, you have an interest, you're a hobbyist, we're really interested to expand those areas. So I think now I will turn it over to Matt for a quick demonstration of OpenROAD.
Okay, thank you, Tom. And let me share a screen. Okay, so OpenROAD is fully automatic, as Tom said, but sometimes you want to either inspect your result, or occasionally, despite our best automation efforts, we don't achieve the result you want, so you want to be able to inspect your design, understand how you could make it better. So I wanted to show you how to use OpenROAD has a GUI that lets you do those kind of things. If you run the automated flow, this is an example of OpenROAD flow scripts. If you look at the results, what you get is a whole lot of text files, or possibly binary files, which are not very easy to debug, right? You read a big def file, you can't really tell what's going on. So OpenROAD-GUI brings up the GUI, same as OpenROAD runs in text mode. This will give you the text mode. -GUI will give you the GUI mode. And there it is. You have a full GUI with a same typical command prompt you would have if you were in text mode and an output window, but you have additional. So I have a couple of designs loaded. I just wanted to show you sort of what it looks like. So here I've loaded up a design. It's been placed, and I've run global routing. So we can see in this design, there's a set of macros, these kind of little black boxes around the corners, and a bunch of logic in the middle. We zoom in, these are all gates. So placed throughout the design. So immediately you can see what your design looks like in a way that you can't from a def file or a GDS file. That's in global routing. The main objective is to reduce congestion for routing. So we have this congestion map display. It's a fairly standard display you see in most commercial EDA tools. And it shows you the density of wires after global routing. Where are you using a lot of routing resource and where are you using less? So we can see the areas where there are not many cells is blue. This is fairly low density. Here, the yellow region is a higher density region showing moderate usage. And here where we have these macros, we can see in red, we have very high density usage. So that tells you immediately most of my routing challenge is getting into my macros, right? Those macros are dense, the routing around them is dense. And that's really the kind of understanding you can get from looking at the tool itself. So that might suggest if you had trouble with routing, you could spread your macros out, you could use bigger halos or channels. Those kind of user level settings would exist to let you examine it. It's a live GUI, so you can zoom in, you can look at the details much more closely. There's a congestion setup, which lets you set the range of congestion you're looking at. I'm looking at from 50% to 100% congestion. If you wanted to see more specifically, you could kind of zoom in and change the ranges, get a more detailed view of exactly where are the highest points of congestion, like here in the middle of this channel. So this particular design is routable, but I just wanted to kind of give you the understanding of you can look at the global routing results and you can understand them in a lot more detail through the congestion map. You can also, as I said, it's a fully live GUI, so you have just your tickle prompt here. You can do any normal tickle command. That's how I ran the global routers. I just ran global route. These are dockable windows, so you can undock them, and you can see your standard text mode output as well. So in this case, you can see that the router was running various iterations, trying to resolve congestion, and eventually it succeeded in reaching zero overflow. That gives you a sense of what you can do in terms of debugging issues in global routing or congestion in routing. There are similar GUIs elsewhere. I wanted to show you a second look at a fully routed design. So this is a different design, fully routed. These are both on Skywater. This is the IBEX design, which is a small RISC-V core. And it's been fully routed. So you can see all the routing layers. It's fully live. You can zoom in and see in full detail what's going on. Of course, EDA layout's very dense, so you need control over what you're seeing. And that's what the display controls here on the left are. You can turn off the layers and see just an individual layer. You can see these are all of your standard cells where they've been placed with their pins. Again, you have full kind of control over individual layers. If we select an item, there is an inspector over here. Make it a little bigger. It gives you information about the object you've selected. And in this case, it's an instance and its name and what type of cell it is. And you can also highlight the individual pins as you mouse over them. And the blue are links, just as they would be in your browser. You can follow the link to the D pin and to the net that it's connected to. So this gives you the ability to sort of walk through your net list. There's a fit button. This shows you this guy is driving up to here. And so it lets you investigate your design. This is sort of at the level of just manually tracing through the design. We have tools to help you kind of go a little deeper, more automatically. For example, there's a timing button here. We'll bring up a timing window. You can choose a number of paths, and you can choose the path. Let's bring it back so we can see. And you can examine a timing path in detail. For example, here starts a clock, and it goes through the network. It highlights the screen as it goes where these guys are. You can see, in this case, we've had repeaters inserted by the resizer as well as buffering inserted. This is for a long connection where it's too long to be driven by a single gate. And this gives you as well your time for each segment and the direction of transition. So this is very much equivalent to if you ran report checks in the text mode version, but here it's also annotated onto the layout. So you can actually get a visual sense of what's going on. You can do both setup paths and you can also do hold paths. The process is quite similar. It gives you a path. Here you can see hold buffers being inserted into the path. Actually, quite a few hold buffers on this path. So this, as well as this is a data path, you can also see the capture clock. This is a path to the register at the end of the path, whereas this clock path is clock path to the register at the beginning of the path. You can choose to expand the clock network and see each of the individual delays put in by CTS. This gives you the ability to kind of go in and zoom in on your design and see what's happening. The other kind of useful things you can do with the display controls, you can control what's displayed by type. So for example, I turn back on all the routing. I can turn off the signal nets, power and ground, leave behind just clock nets, and there's my clock tree. So I can quickly see my clock tree. In addition, we have a find option, which I'll show you a kind of a useful trick. You can find instances by name like clock star. And if we select all those are all my clock buffers. We name them consistently, so that will find every clock buffer in the design, along with your clock nets. It's a pretty easy way to get a picture of your clock tree. Tom showed you in the slides. This is kind of how you can do it graphically. If you do it pre-routing, you'll see it looks a little bit more like star topologies because this is a post-routed version. So this is the kind of inspection you can do. Again, even if you turn off the visibility, you can still see the selection of where are all the clock buffers and how are they distributed through the layout. The other thing I wanted to tell you about is in OpenROAD, when the tool starts up, it will read in your home directory a .openroad file, as many tools do. You can create your own buttons. So this create toolbar button, you can see this PG is this button here. These three buttons are actually not part of normal OpenROAD. I created them myself. You can create your own buttons for any commonly carried out action. Give it a name, and a script is just a tickle script, a set of commands to run. So here I'm using the commands that let me turn on and off visibility. So for example, I get power and ground's current visibility, and then I set it to the opposite, which lets me toggle on and off power and ground. So if I'm looking at the whole design, I often don't want to see power and ground. I can just toggle them on and off. Likewise with instances, I may not want to see the fillers. I can have a command or a button to do that. So you can create your own customized usage models. It can be any script you want. I mean, these are kind of graphical scripts, but you could have a button that says do global routing. So all of those are available to fully customize the GUI. So this is kind of the general high level. If we zoom in and we look at this, there are also detailed options like there is a ruler where you can measure distances between objects. Pretty helpful if you're looking at DRC violations. You say, are these objects too close? What's the rule? You can kind of measure objects. So it's a K hotkey, and it has object snapping. So it will attempt to snap to the edges of objects. You can turn that off if needed. So it's pretty helpful. The timing GUI and the congestion GUI are probably the most powerful for debugging, as well as just simply being able to trace the layout and look at the patterns directly. I'm glad to give more time to any demo someone wants to see on any particular features, but this is the high level.
So is that the end of your demo, Matt?
Yeah, that was the end of what I was going to had prepared, and I think we wanted to leave
Okay.
a few minutes if people have any questions about either Tom's talk or my demo.
Yeah. Yeah, let me put the IRC banner up as well.
DRC results, you can. There's a DRC viewer here.
No, sorry, I'm putting up IRC, the IRC channel, because we've got the chat on in YouTube and the IRC and the matrix. But yeah, we actually just did get a question. Are you able to see DRC results in here? And
Right,
make
so there's a
necessary
DRC
edits?
viewer. This design doesn't happen to have DRCs, but there's a load button, and you would be able to load up a report file, which is basically generated by Triton Route, the detailed router of OpenROAD, and it will give you a list of violations. It will also load, if you run through KLayout, you can generate a JSON from KLayout, and we can load that as well. So we can support either tool. You could, in principle, take a commercial result and load it as well if you converted it into one of the formats we support. We don't directly support commercial DRC format outputs, but we do support our own on KLayouts. And yes, there's a viewer. and I'd have to generate a design that has a violation in it, but basically gives you a list of short, spacing, and will show you the interactive objects.
Great. Okay. So I don't think we've got any more questions as yet on the YouTube channel. So I'd just like to say thanks very much, Matt, for your time, and Tom for the presentation on OpenROAD and the OpenROAD GUI. So let's hear it for Matt and Tom in the comments and on the Element chat. Give your appreciation up, send a thumbs up or something. Yeah, thanks again, Matt.
No problem. And I do see one or two questions about interactive options. You can interactively, from the inspector, edit directly, like placement. You could change this to and move it around. It doesn't have a fully live drag and drop kind of thing, but you can do surgical changes. You can also delete an object completely. So there is that. There's also from Tickle, you have the ability to modify the database. So all the database commands exist and would be live to the GUI.
And I see Tom Spyrou has jumped into the chat on IRC, so he's also answering questions there about OpenROAD. One other question for you is, what about documentation? Do you have a like a getting started doc for this?
So the GUI does have a section, and we should mention OpenROAD itself has documentation. If you look in the GitHub, and we have a read the docs, which is generated from GitHub, you can find it both places, and there is a GUI section. I would say it describes the commands of the GUI pretty well, but the interactive part is a little bit less documented and have typically been done live, but we probably should write a little more of the interactive. This, by the way, is an easy area for somebody in the community who wants to jump in and try and improve things. We absolutely welcome documentation improvements, but it's an area that we probably should do a little more description of. But certainly all the commands of the GUI are well documented. Maybe
Yes,
not all the little buttons and tips and tricks that I've been trying to show. Like there's a right mouse button that lets you do many of the same options that are up here. Those sorts of things probably need a little more documenting.
Yeah, so I mentioned earlier how there's never been like lower barrier to entry to get involved with ASIC stuff. And that goes also with contributing as well. So I would say that probably 70% of my contributions are documentation fixes. So don't feel free to jump in with fixes for documentation. That's always appreciated.
I think it's maybe also worth mentioning, some people mentioned K-layout. The main difference between the OpenROAD GUI and say working in K-layout is K-layout works really in the GDS world without connectivity, whereas OpenROAD works more in the world of left and def with connectivity. So connectivity is much more naturally expressed here. If you highlight a net or the like, they don't really exist in traditional GDS views, right? That's sort of limitation of GDS. Here, a net knows what it's attached to very directly, or often GDS, you have to geometrically derive that. So they are somewhat different use models. So I think the two GUIs are kind of complementary. K-layout has certainly a very nice GDS viewing GUI.
That was actually one of the things that got me interested in the OpenROAD GUI was I was trying to, when we had the problems with MPW1 clock tree, and I was trying to trace the clock tree from the GDS in K-layout. And to do that, you have to load the tex file, and then you need to trace and build the connectivity.
Right. Yeah, that's the limitation of the GDS format. It's really designed to just represent polygons and kind of be your end state for tape out, whereas this is really more your design tool state in left and def where you actually have the connectivity. Purely analog designers, that's a different story, but for kind of place and route style designs, it's usually a little easier to work in the left def space.
Excellent. Well, thanks again, Matt, for your time today. It's been super awesome. And yeah, if you want to have a chat with Matt or get in contact, then the place is probably the GitHub for OpenROAD, or join the Skywater Slack and get involved in the OpenLane channel.
Yep.
Great. Okay, thanks again, Matt.
No problem.
So now we're moving on, and we're going to take a look at some security stuff. So today we kind of got a bit of a security bent in the latter part, and tomorrow we've got a bit of an analog exploration. So today on the security side, we've got David Hulton and Joe Fitzpatrick, and we're going to kick off with David Hulton, who couldn't make it, but he's sent me a video, which I accidentally started playing when Tim was talking, so apologies, Tim. And I'll just start this off in a minute. So I met David because he came on one of my courses. He runs Tour Camp, he's got a bookshop. He's involved in the security community, and he was doing some interesting work with electromagnetic fault injection. And he was using some of the new AE tools developed by Colin O'Flynn, one in particular called Chip Shelter. And the idea is you try to upset a microcontroller that's running to get it to do something you want it to do. For example, if you've got like an RSA encryption, you've got a certain number of rounds. If you can jog the round counter just at the right time by giving it a little spark, then you can get it so it quits after one round and the security is much lower. So he was doing a bit of investigation into that with an FPGA design, and he taped that out on MPW2, and this is his presentation.
And for a little bit of background about myself. Hello, I'm here today to talk about fault injection attacks and how to defend against them. My name is David Hulton, and for a little bit of background about myself, I started the TourCon Security Conference over 20 years ago and was involved in an FPGA company for over 10 years where I hacked various hardware devices and crypto systems. My company was acquired by Micron in 2015, and since then I've started their hardware red team where we develop attacks against hardware and get to play with some really fun toys. Just as a disclaimer, all of this presentation is my own research and opinions. So first off, the whole point of glitching or fault injection is to trick a device to let us do something we're not supposed to do. I'll go over a quick intro into how it started and the different ways to glitch a device, and then ways to prevent people from doing it to your hardware. So glitching has been around for a long time, and I would argue since transistors were invented, people have tried messing with the physics of them to get out of some tricky situations. For example, in the 90s, satellite TV hackers, when faced with their pirated cards being disabled, came up with ways to glitch the voltage to get them to skip out of an endless loop. And since then, techniques have improved and mainstream products have been hacked using these methods. So some of the things you can do with glitching attacks are things like dumping protected firmware, which you can then reverse engineer. You can upload backdoored firmware and extract keys, open up debug modes. But also if there's code in the firmware that implements security protections, you can use glitching to bypass those and potentially gain code execution on the device. So it's a pretty big issue. Just as an example, one recent example, this is a glitching attack that was presented a couple years ago by Dmitry Nedospisov, Josh Statko, and Thomas Roth. They showed that the firmware readout protection of the STM32F205, which is a very popular STM32 chip, could be bypassed using voltage glitching. To do this attack, you have to be able to affect the core voltage of the CPU. So if you look at the power schematic in the data sheet, you can see that the internal voltage after the voltage regulator on the chip is actually routed out to bypass capacitors outside the chip. By connecting to these pins, you can directly change the voltage for the CPU using a custom power supply or MOSFET and various methods like that. So now by precisely dropping the core voltage when it's reading out its readout protection register out of EEPROM during boot up, you can corrupt it and cause the device to think it's in a less protected mode. Then by checking to see if JTAG is open or other debug mechanisms, you can verify that the device is now unlocked and some of the debug features can now be accessed. But there's some of these STM32 chips that have the internal core voltage supplies that aren't routed externally. So how do we do this type of attack on them? Well, one of the most popular methods is to use electromagnetic fault injection, where you discharge hundreds of volts through a coil placed above the chip. And this couples to metal loops in the package or die and induces voltage changes, which can create similar effects, but much more localized. And with this type of attack, you typically need positioner. You also need to tune things such as the discharge voltage, size of the coil, whether the coil is wound clockwise or counterclockwise, and the size of coil. But it's a very powerful technique because you don't typically have to actually modify the device or drop probes down on it even. So this has become very popular. And there's devices like the chip shouter, which for about $3,000, makes it relatively inexpensive for people to play with. So here's an attack being performed on an STM32L151 using EMFI using this chip shouter device. And it demonstrates that we can extract the firmware using this same type of attack, but with EMFI. And then now, after we've dumped the firmware, we can reverse engineer it, figure out how the device works, and potentially extract keys and other secrets to just bypass all the security of the device. Another method for fault injection is something called body biasing injection, where we place a needle on the back side of the chip and bias the substrate for that particular part. And this effectively changes the reference ground for a very localized part of the chip and can affect the operation of transistors and other memory below the needle. So these pictures show Colin O'Flynn's recent research into BBI, where he published results and schematics for an inexpensive BBI device. And we've actually gotten really good results of this using this in our lab. And then at the more expensive end of fault injection, you can use lasers to induce faults. There's commercial systems that are quite expensive, like the one shown here, but also homebrew ones that people have had really good luck with using laser pointers or tattoo removal lasers. And the basic idea here is that when transistors are exposed to photons, it changes the conductivity characteristics and allows you to also induce various faults that are extremely precise and localized in certain parts of the chip. So now the big question is, what do we do about these types of attacks? Turns out that during normal program execution, there's many unexpected places that can be vulnerable to fault injection, and it's often really hard to predict. So there's a number of simulators out there like FISIM and TrueCode, which are provided by Riskier. And they can help you identify how glitchable your firmware is. And then there's also a number of firmware mitigation strategies that have been documented by companies like Riskier that you can use to make your firmware more resistant to glitching. But one of the problems with this is that firmware mitigations can never fully 100% make your device safe. So there's companies and many research papers out there proposing solutions for detecting glitches in hardware using hardware circuitry in your chip. But looking around, I couldn't find any open source IP for doing this, and so I thought, why don't I try to solve this problem? So back in June, I took Matt's 0 to ASIC course and didn't realize that there was still a possibility of submitting a design just 10 days later for MPW2. So I quickly decided that building a glitch detector would be an interesting thing to try and a relatively small project that I could probably complete in that amount of time. So looking at the different papers out there, there was a more recent one by Jacob Breyer, Shivam Basan, and Wei Hu that looked very promising. The basic idea is that they create an oscillating data signal based on a clock, and then use a phase detector to see how in phase it is with the clock. So if there's a disturbance in the data signal or the clock, then it'll be out of phase and the detector will generate an alarm. And then we can use that to tell if we're being attacked or not with one of these fault injection techniques. So I implemented the strategy outlined in this Hogue phase detector paper, simulated it, and then also built it for a Lattice ICE40 FPGA, and tested it against EMFI glitches. My design adds a latch to the alarm signal, so short glitches can be detected, and also added a counter so we can have some measure of how many glitches have occurred. So if we take a look at an oscilloscope capture of injecting EMFI faults. You can see the EMFI waveform at the top, and below it, it's being detected and latching the alarm, and our alarm count signal is increasing at the very bottom. So now that the design is submitted, I'm now waiting for chips to come back next month so we can test how well it's able to detect glitches, and hopefully now have IP that open source secure processors and the industry as a whole is able to use to protect against these types of fault injection attacks. Overall, I think the OpenMPW program is just an incredible resource, and just the thought of being able to go from the concept to tape out, even for a really small design like this, within a matter of days, using all open source tooling is just astounding. And I also just want to give a huge thanks to Matt Venn for really evangelizing this new resource and making it so easy for people new to VLSI design to get into it and just create really amazing results in just extremely short amount of time. So in closing, I want to thank you all so much for listening. If you want to learn more about my glitch detection adventures or have follow-up questions, feel free to connect with me on Twitter at 0x31337. And I also encourage you to come to some of the hacker events that I organize, such as TourCamp and TourCon. They're happening next year. So thanks again, and happy hacking.
Excellent. So let's get some love for David in the comments. Give a thumbs up and say thanks if you liked that talk. I found that super interesting, and it's really great to see this kind of stuff coming out of papers that are then getting tested on FPGAs and even on ASICs as well, which is, I think, going to be really great step forwards for doing security-based stuff. So before we have our second security talk with Joe Fitzpatrick, I want to introduce Lucas. I was very fortunate to be invited to OstroChip about a month ago, already seems like a very long time, by Harold. So I'd also like to say hi to Harold if you're watching, and your lab. That was a really great experience, really good presentation, and a great visit around the campus. And while I was there, I met Lucas Klemmer, who's developing a new tool that is going to help understand better the kind of big dumps of traces that we often get when we're designing digital designs. You do some hardware design, you simulate it, you get thousands of traces, and then it's kind of difficult to see what they're all doing. So what Lucas is working on is a tool to make that more understandable. So I'll just invite Lucas onto the stream. How are you doing today, Lucas?
Hi, Matt. I'm doing great. Hi, everybody.
Yeah, so all ready to go?
Yeah, I will share my screen.
Share your screen, yeah.
So you can see my presentation?
Yep. Okay, so I'll say bye-bye and hand over to you. Oh, you want to switch into presentation mode to make it full screen?
Yeah, I am in presentation mode already, but
okay.
I will try once again. Okay, then I will do the backup solution.
What's the backup solution?
The PDFs.
Oh, the PDF, absolutely classic. Okay, we're rolling with the PDF.
Okay, you can. I hope you can see the presentation now.
Yeah.
So, hi again. My name is Lucas. I'm a PhD student at the Institute for Complex Systems.
It's just gone.
It's just gone. What is happening?
Oh, there it is. No, we got it. There we go. It's probably my fault.
Sorry.
I'm very bad at driving this.
So, yeah, I'm a PhD student at the Institute for Complex Systems, and today I want to present a new WAL programming language which enables programmable waveform analysis. So I want to start this talk with a little thought experiment, even though this is a bit unusual for computer science, but let's assume you developed a brand new design which is going to be included in the next OpenMPW shuttle. So tape-out day is approaching. You are very excited. However, the last test showed that there are some short performance drops from time to time. And of course, you have to fix these, find and fix the cause. So what do? You open a good old waveform viewer and start debugging. So here you are in a waveform viewer, you open everything up, and what do you see? Well, this is way too much data, this is information overload. So you zoom in a little. This is better, but still too much information. Some signals we cannot even see the values. So we zoom in once again. But now we are too close. So now we completely lost the context of where we are. We can't even see what happened 10 clock cycles before. What I want to say here is that waveforms contain incredible amounts of information. Information about the performance of your design, correctness, data control flow, and also optimization possibilities. But there are some very hard problems there. So the first problem is that waveform debugging is a 100% manual task. Whenever you do a new simulation, you have to start from the beginning. And of course, this is very tedious, and navigating inside the waveform is slow. And really, you can only see a very small slice of the simulation at each time, which limits you to basically debugging simple problems only. So maybe the major problem here is that we cannot automate this, right? So normally here would the animation say, or can it? So we think we can with WAL, our new waveform analysis language, which is a domain-specific language that really lets you express the problems that we face in hardware development. It features specialized language constructs for the hardware domain. For example, the signals you have in your design are first-class citizens in the language. You have access to time information, which we don't have in other general-purpose programming language. You have information about the hierarchy, and also about logical relations between signals, for example, the signals of a bus. And really, you have more power here. You have more power than, for example, a system Verilog assertions. You can do more than just expressing true or false expressions. Really, you have the power of general-purpose programming languages. You can define new functions. You have lists. You have hash maps. You have everything you know. And you can even call external libraries. And because we implemented all in Python, this gives you instant access to 1 billion Python packages. So if you ever wanted to feed your waveform data to some neural network easily, you're already set up. You just need to import TensorFlow. I want to introduce some very simple WAL code here with a basic example. And let's say we have a bus with a request acknowledge interface. I guess everybody has seen something like that here. And we want to calculate the average delay on this bus. So the average delay, how long one request has to wait before it is acknowledged. And to do this, we can see two interesting states. So the first state is obviously the waiting state. So the interface is in a waiting state whenever we have a request set to 1, but the acknowledge is still set to 0. And we can express this using this WAL expression here. And I guess at this level, everybody understands this. And the opposite of the waiting state is the sending state. So the bus is sending whenever we have a request, and we also have an acknowledge. And what we want to do here is we want to count both states. And in the end, we want to divide the number of waiting states by the number of sending states, which will give us the average latency. So because we want to do this on a complete waveform, and here we can see, here we have 40 ticks, but in reality, you maybe have 10,000. So it's obvious you cannot do this by hand, realistically. So we want to go over the complete waveform. So we wrap our expression in a whenever operation. And this says, whenever the clock is 1, do the operation in the body. And what is the operation in the body? It basically detects the waiting and sending states here in this when operation, which is an if operation without an else clause. And when it detects a state, it increments a variable. And after we are done processing the complete waveform, we will just divide our states and print the result. And hardware designs most of the time contain many structural similarities. For example, often we don't have one of these handshaking buses, but maybe 2 or even 10, we don't know. So this is of course ideal for writing generic code. It enables us to take the same code we have written before for one interface and now evaluate it on any interface, on any number of interfaces. And I want to show a real quick example how we can do this here. And for this, while we have the grouping feature. So what we first do is we detect all groups that contain a request and an acknowledged signal. And then we take the exact same expression as before, but we modify the signals quite a little bit. Namely, we append a hash in front of the signal name. And what this will do, this will evaluate the expression from before twice for each bus. But when the expression is evaluated, the hash will expand the signal name so that the correct signal is called. And with this little modification, we can extend our expression from before to the complete design. And really, if you add a new instance of the handshaking bus, it will work automatically. Of course, we want to show that WAL is really applicable to real-world problems. And for this, obviously, we solved our own problems first. So I have 2 examples here. In the first example, we developed a Python application with a GUI. And this is a general waveform analysis program. You can load any waveform that you have, and WAL will detect XI buses contained in the waveform, any number. It doesn't matter. It doesn't has any. You don't need to provide any information really. And for each interface it finds, it will render some neat graphs about the performance and some other metrics. And then we had another problem. We were working with the VexRisk-V processor, but we had a hard time understanding how exactly the processor was working internally. So we wrote a very little WAL script. I think this is 50 lines of code, and it renders a nice HTML website with a table that shows the pipeline stages, and you can see the instructions flowing through the processor, which is also color-coded. And we also added some warnings or errors which were detected during the execution of the program that we were running. So this all was possible with just a few lines of code. To wrap things up, waveform viewing is highly manual, and there's so much we can get from waveforms. And with WAL, we can do programmable waveform analysis to do, for example, data aggregation or data visualization, or really we can express any complex queries that we or you want. And WAL is, of course, available as open source on GitHub, and very soon it will also be available on the Python package index. And if you want to get more information about WAL, there's a research paper available on our institute website, and we will also do a presentation in January at the ASP.DEC conference. So if you have any more questions, please feel free to write me an email. I will be happy answering you, and I will also be happy getting to know the problems that may be good problems for WAL. Yeah, I think that wraps up my talk.
Thanks very much, Lucas. That was super interesting. I think I'm really looking forward to using that tool myself. If you've got any questions or you want to know more about it, then feel free to join over on the Matrix or IRC, and I put the links in the description of the video now. So let's hear it for Lucas. Just give some thumbs up and some thanks in the comments. Let him know that you enjoyed the talk. And thanks again, Lucas, for your time. Really appreciate it, and hope to see you again sometime in Austria.
Yeah, sure. Bye.
Bye-bye. Okay, so we're coming up to the last presentation for the evening. And just before we start that, I wanted to remind everyone who's in the US, or most of the people in the US, that your daylight savings time is changing. So Although it will feel like we start at the same time tomorrow, it will actually be an hour later or earlier or something like that. So use the calendar links, double check you get it right. I'll be sending out an email with a 1 hour advance warning. Hopefully you won't miss it. So to introduce our next talk, Joe Fitzpatrick from Securing Hardware is pretty well known in the security community. I got to know him a bit through he was very kindly helping me out with my 0 to ASIC training course, giving me some reviews over there, along with Chris Gamble, also another online educator, also helped a lot with me working out what I wanted to do with my course. Yeah, just a real good, very generous guy. So I'd just like to bring him onto the stage now. Hi, Joe. How's it going?
Pretty good. How you doing?
Yeah, I'm doing good, thanks. Yeah, we're all ready to go?
Yeah, I'm all ready to go.
Okay. Could you turn up your volume a little bit?
Sure, I can do that. Let's see if that button does it. Can you hear me now? Can you hear me now?
A very low.
Oh, what did I
Nice.
change? I tested it yesterday. Is that better? Is that better?
That's fine, yeah. Yeah, we'll get
Okay.
feedback in the chat, and
Okay.
I'll let you know if it needs to change. All right,
Sorry.
take it away.
Okay, awesome. Thanks for having me, Matt. Glad to be here. Glad to talk a little bit about hardware security. As Matt said, I spend a lot of my time doing hardware security training, but I generally train software security people on kind of low-level hardware, learning how to find JTAG, UART, SPY. But my background, I worked at Intel for many years, and while I was there, I worked on silicon debug, speed path debug of desktop server CPUs, DFX, using DFX to do that stuff. So I've seen a lot of the insides of the hardware before going on into the security side of product security at Intel, before going out on my own and teaching hardware security to the InfoSec community that thinks that, oh, it's hardware, it must be solid, it must be trustworthy, it must be, it must work. We all know the case that, beneath the full stack that they talk about is the full stack that we deal with, the hardware down to the silicon with the IP blocks and everything. So I just wanted to clarify, you may think I was going to go through 101 ways to flip bits. It's actually, in case you want to worry, this is the 20-minute version. This is the 101 ways to flip bits and 101 ways to stop it. And when I talk about flipping bits, I basically, you take 101, you flip it, and you get 010. So that's the kind of bit flipping we're talking about. There is a longer 2-day version, the, hex 101. Perhaps there's the signed binary, but we don't know how that's going to turn out. More importantly, I was really excited because just last week, the 2021 CW Common Weakness Enumeration vulnerability list weakness list was posted by MITRE. So what they've done is they've gone through and they've taken tons of these common hardware weaknesses and kind of given them code names, right? This is not specific bugs. That's the common vulnerabilities you might hear about. This is the common weaknesses. Like a lot of bugs seem to fall into this category. And these are the top 10 hardware weaknesses for 2021. So you should all read this list and become pretty familiar with it. But what really is important to me is the fact that whoops, I'm writing in white. Let me change my color to write in red so you actually see it. So right here, improper prevention of lock bit modification, right? So I'm talking about flipping bits, not just any bits. I'm talking about flipping lock bits and the bits that they're supposed to be locking. So what does that mean? There's some details on each of these, along with some examples for many of them. So the product uses a trusted lock bit for restricting access to registers, address regions, or other resources, but the product does not prevent the value of the lock bit from being modified after it has been set. So this sounds like a bad idea. Here's an example. Whoops. Actually, I was just going to point out, that's the one I'm choosing, but there's a lot of other references to lock bits in these top 10 and even other common weaknesses. So I'll go through a few of those. So what's a lock bit? It locks other registers when it's set. So we have this critical register that's something important. Maybe it's the power supply setting or, something, a key that gets used. And you want, once this is set, you never want it to be changed. You don't want end users, less privileged software, anything to go and modify this after the boot up and initialization has happened. Whether the initialization happens from mask ROM, ucode, microcode, anything like that, or even user code. This is basically setting up a situation to be a known context that is executing. So we have a lock critical register bit, and we just set that to true. Now, once we've set lock critical register, right? We go and we try and change it, try to hack the value, and it doesn't work, right? Because that register is suddenly locked, okay? Seems like that should be sufficient, right? But, hackers are creative, so we'll go and try this. Okay, so that first attempt doesn't work, but what happens when we just go ahead and we change that register to false, right? That that lock critical register, if we change it, we can suddenly modify the register below again. So we got to do a little bit more than this. We need to actually lock the register that we're locking with. We need to make it somehow secure, so once we've locked it down, it doesn't get unlocked. Again, my experience was at Intel, and the convention there was basically reset. Everything gets locked and set until reset. When the system resets, it has to happen again anyway, so it's all cleared. Depending on your target, your ASIC, your architecture, your design decisions, that might not be the case. You may have operating modes where certain things get reset or not, but that's mine. My assumption I'm going to go with. So what we do is we have what's called a write once lock bit. Okay, and this is great because we set our value, we set our lock register, our write once critical lock register, and when we try and change the value of the critical register, it doesn't change because our lock register is locked. Right? If we try and change the value of the lock register itself, it doesn't change because it's also locked. It's a write once register. Once it's been written once it has a value, it doesn't change. And so when we go and try to modify that register again, we can't do it. So we've been defeated as an attacker trying to maliciously change registers. However, there's a CWE for that, right? Improper prevention of lock bit modification. So if the product uses a trusted lock bit for restricting address or other things, but does not prevent the value from the lock bit from being modified after it's set. That's what we talked about before. But actually, let me go into a little detail here. An example. So this is one of the published examples, which is great because I know some examples I probably shouldn't talk about, but when they're on MITRE's website, I can talk about them, right? So we have this this temp sensor lock register, right, and we can lock it, and then we have this hardware shutdown register, which enables hardware shutdown on critical temperature detection, right? However, anybody can enable or disable this despite the fact that the sensor is supposed to be even locked. So the vulnerability, we basically need to make sure we lock the relevant register. So making sure you're locking the relevant things is pretty important. But even if we went so far as to set it to this write once situation, write once saturation, right? If we can sneak in ahead of time, like on a PC, if this is what the operating system does and we do this in the BIOS, right, or something like that, what if we go and we change our critical lock register to false, right? Now, that means it's a write once. We wrote a 0 to it. And now critical register is not locked, right? And then we later on go and write true to it, okay? The problem is it was written once already. It took the first value, it keeps the first value, it doesn't change that. That's a bad thing because we can then go and change it again and then try and fix it and then change it again. Over and over again, we can just modify the register because we've locked it open. Again, there may be cases when you want this to be possible, when you want to basically set up a system to not be locked down or unlocked permanently. But typically, this is not the behavior you want. So what we usually have is basically a write once, right? So you can write a 1 to it one time. And so if you write 0 to it, it doesn't matter, right? If we did that before we write equal to 0, it doesn't matter. It's not a 1, so it's not locked. So basically, the lock register locks itself. Here we go. We write it to 1. We can't change it. We write it to 0 again. It's already been written 1 once, so it stays 1, and it's good. Okay. But then, of course, we got to figure out a way to bypass it, right? The reality is we don't always write discrete values to registers. Oftentimes, we've got this lock setting register, and that lock setting might be a combination of logic that combines, a bunch of stuff with logic from different paths and chains. So it may not be a direct literal value that we're setting things to. So if we can influence the value of lock setting, right, then we can go and not let this lock actually happen, right? And so when we change it to false, it doesn't actually matter because we still have access to that register. So there's a CWE for that, right? The hardware design control register sticky bits or write once bit fields are improperly implemented such that they can be reprogrammed by software. So software or other combinational logic. And here's an example of a problem and a fix, right? Over here, we get down to the spot, right? Where we basically have that data in. That's the write once status that we set it to. And the solution is basically to say, nope, we're just writing it to a 1. So basically, anytime you write to this register, you're locking it. Okay, so it doesn't matter whether you write a 1 or a 0. If you write to this register, you're locking it, which kind of removes that complexity, right? So we've got this improved write 1 once bit, right? It locks other registers and itself when it's written. It doesn't care what the data is written to it. So the critical register, we set a value, right? We set our lock setting. It doesn't matter what this value is because it's a write one, set when lock, set when written. And of course, there's no change. We can do as many more writes to it as we want. It doesn't matter. There's going to be no change because once it's been written once, it's set, it's locked. That's it. Doesn't matter the value you write to it. It's locked. So we got this improved write 1 once lock bit. But then we got to think like, okay, we talked about what really is that lock bit. Is it combinational logic or something? But what really unlocks the target register? Is there anything left that can still unlock it? A lot of times you have debug modes that do exactly that, right? Luckily, of course, there's a CWE for that. Let's see. Number 1, 2, 3, 4. Hardware internal or debug modes allow override of locks. Okay, so basically we've got debug modes that are going to give us some combinational logic that say, okay, so if write and lock status and scan mode and debug unlocked, right? So we have this combinational logic in there. And it basically says, oh, if you are a debugger, if you have your debugger attached, if you're in JTAG mode, if you unlocked JTAG or any of these like scenarios, then suddenly your locked register is unlocked. This might be necessary for hardware development and design and getting things up and running, but it's probably not the behavior you want typically. So how do we lock down the debug access? The typical answer is we authenticate the debugger. And authenticate can be a loaded word. It could mean that we do this cryptographically, right? It could mean that we have a key system, a device-specific key. We need to generate, all that fancy stuff. That's hard. That's complicated, but that might be what our product requires. It could just mean physical access, right? So this is the difference when we say things. We say, okay, we make no effort to protect against attacker with physical access, right? If we make that statement as a hardware designer and pass that on to the software users of our device or hardware users of device, that's good information. They'll know not to put trust into this thing. If, however, on the other side, we make a marketing statement that says, oh, your keys are safe in our chip, right? We're making some pretty strong statements about physical access without even saying the word physical access. We're saying that, oh, you can take this chip, you could put keys in it, and no one's going to be able to get them out. You don't explicitly say that, but that assumption is loaded in there with that statement. Okay, so locking down debug access, how do we get around that? Well, there's a CVE for that too, right? CWE 1191 on chip debug and test interface with improper access control. How are we gonna lock down debug interfaces? We'll use lock bits, right? So we're kind of going around in a circle where we have a resource we want to secure, right? We have a control bit that we can use to secure it. And then we have all the ways we can actually influence that control bit. And then all the ways we can influence the access to it. So here are my recommendations, right? This is a security detail, right? When you're getting your first chip working, like this isn't your priority. But if you're going to get to the point where you're going to take an open chip design and trying to make it into a product, you're going to need to ship it with some security expectations, right? Say out loud that we make no guarantees of anybody having physical access to this chip. That's a good start because people aren't going to have false assumptions about what your device does. People aren't going to buy your chip, put it into a device, and then sell it with that unwarranted security expectation. Now, let's say you do need to lock down some details. Let's say you want to implement some sort of secure boot or firmware protection or integrity checks, right? Use locks. When you do that, document them when and why you use them, right? So documenting when and why you use them, is helpful for the designer of the chip, as well as the person who's writing the documentation, who's telling users how to use this chip, right? And that's important because if you don't educate or encourage users to use those lock bits, they don't happen. So an ASIC example, this is from an XP datasheet. This is a chip that I encountered on a PLC that I was taking apart, Programmable Logic Controller. And the Programmable Logic Controller had the JTAG pins visible and exposed from outside of the device. So you could walk by this PLC mounted on a DIN rack and walk up to it and pop something in that would touch those JTAG pins and talk to the device. Do you think the code readout protection, that the JTAG granularity setting was set? No, it wasn't set at all. They didn't expect it to be an issue. They didn't really understand it. Now, going back, they might reconsider that. They might say, oh, well, maybe we should disable JTAG once our device is provisioned. There's a good reason for that. We have some granularity. We have the CRP 1, 2, and 3 modes that we can set it to. And CRP 3 means no future factory testing can be performed on the device. When you're designing a hardware device with a chip, you read this and you say, oh, my warranty is void if I set this bit. So I'm never going to set that bit because I'm never going to be able to say, hey, NXP, you gave me some bad chips. Like, well, can we test them? Like, well, the CRP3 is blown. You can't actually test them. Like, oh, well, too bad. Out of luck, not a problem. So what we've got here is granularity. You don't want to have just one lock bit that locks your whole system. You want lock bits that are relevant to exactly what you want to lock down. So what do we have? We have a CWE. Insufficient granularity of address regions protected by register locks. Okay, so specifically address regions in this one, but in general, lock bits, right? If you want to lock down a range of values, come on, next slide. Here we go. Next. So we might have a bunch of lock bits, right? And then each of these lock bits, all 32 of these lock bits, each lock a specific region of memory, right? This might work out really well. This could be great. But in this case, each region is 4K, right? Well, if you don't want to lock 4K of memory, you only want to lock 1K of memory. Or, you need access to a specific 1K of memory, which means you can't lock the adjacent 1K regions, right? There might be a situation where this granularity isn't good enough. You might need 64 bits. You might need more. You might actually need less. It's a balancing act to get like the level of granularity that you need to lock things down, along with at least reduced complexity so users actually use those lock bits. So revisiting my recommendations, document your security expectations. Use locks when you do. Document when and why you use them, and educate your software users, the downstream everyone, when you should be using those locks. I do have a checklist that has been evolved over time, like our checklist. What locks to apply to which registers? Who can set the locks when? Can the locks be unset and why? When are they cleared? Locks are in which power, clock, and reset domains, right? That configuration bit itself, what domain is it stored in? Like if you remove power to one portion of the chip, can you wipe your lock bits without resetting the part? Can your configuration be cleared without clearing the lock itself? If you want to go and test this, right, you write some test cases. You just basically try accessing the lock, try clearing a set lock, messing with the lock configurations, then go through permutations. You might have a series of lock bits. Make sure all those lock bits, the correct lock bit is used on right target. And if you have combinations, like if you set all but one of the lock bits, does it have effect on how the others work? Yes, you can go and look at the code to figure out how all this code, the Verilog, the HDL, the gateware, to see how this all works. But it never hurts to go and try it on hardware as well to make sure it matches. So that's what we've got for you. To summarize, we basically got n ways to flip bits and n-1 ways to stop it. You can tell that I've got fewer ways to stop it because that's my approach. I'm looking to break stuff as opposed to your approach, which is probably trying to build stuff. You'd much rather have the n+1 ways to flip bits and the n ways to flip bits and the n+1 ways to stop it. So perhaps there's some research there and room for future opportunities. Are there any questions? Let me peek quickly.
Great talk. Thanks, Joe.
You're welcome.
Yeah, so let me just put the banner on again. There we go. I also put the links to the IRC and the matrix in the description of the video. So if you've got questions for Joe, then feel free to ask them over there. And could we get some thanks and some thumbs up in the comments if you enjoyed Joe's talk? Joe, that was really good. Thanks so much for your time and coming on today. And
thanks for having me and thanks for organizing.
Yeah, and if we've got any questions, then we'll take them over in the matrix or the IRC. So thanks again, Joe, and I'll catch you around.
Yep.
And that's the wrap up for tonight. So thanks very much for joining. We'll stay around for a bit in the matrix and the IRC channels, having a chat if you want to join. Otherwise, see you at the same time tomorrow if you've already finished with daylight savings time, and an hour different if you haven't, hopefully. So look forward to seeing you then, and let me just put up the what we've got happening tomorrow. So day 2, Mohammed Kasim is kicking off, the CTO from eFabulous. Then we've got a little analog section, Thomas Parry and Pepijn de Vos. And then we're going to take a look at another open source RTL to GDS2 toolchain, and then an overview of the LibreSoc project. And then we're finally going to finish up with John McMaster, who's got some great microscope shots already of the MPW1 silicon. So you don't want to miss that. So hopefully see you tomorrow. End broadcast.